Our next presenter is Saeed Jafarzadeh, and he's going to be talking about his project Hyperscale Data Centers Powered by Renewable Energies, where he's working with Anthony Bianchi. Saeed.
Thank you, Tony. Okay, I assume you hear me well. I'm going to start by sharing my screen. And so my name is Saeed, and this talk is about hyperscale data centers powered by renewable energies and the challenges that exist there. What I'm presenting today is not my only my work, but I have Dr. Bianchi, a computer scientist, as a teammate, and also the majority of work is that I'm gonna present is done by our undergraduate student Peyton Herrera, and we are very proud of her work. Let's start by discussing hyperscale data centers. By hyperscale, we mean the data centers that have the ability to scale hardware resources very rapidly. These data centers are needed for cloud and big data storage, and their need is more and more coming the more and more we use data online. There are typically more than 5,000, have more than 5,000 servers, at least 10,000 square feet in size. Many of them are in the US. The US has 44% of those data centers, and usually big tech companies, Amazon, Google, IBM, Microsoft, they own and run these large data centers. Now, as I mentioned, over time, like you see here, the number of these data centers and their operation increased, and since they consume a huge amounts of energy, as a result, their overall carbon footprint has increased too. And what happened is that many of these companies and these data centers try to start using renewable energy centers, renewable energy sources, or plan to use them. So we see more and more renewable energy in these data centers, and well, to be able to hedge against the intermittency of these systems of renewable energy, they rely on energy management systems, and that's the focus of our research, these energy management systems. Let's talk about interruptions in data centers. For every IT outage for a business, it costs an average more than $5,000 per minute. In terms of a range per hour, we are looking at $140,000 to $540,000. And out of businesses that had a major data loss, 43% never reopened, 51% that reopened, they closed after 2 years. They couldn't survive, and only 6% can survive long term. So it's a very serious issue for businesses. So these interruptions, and they are not, they don't happen very often, but they happen enough, and they are significant enough, just like you see on this picture on the right side, that we have every year instances of problems, significant problems with data centers. So introducing renewable energy, relying on energy management system, we don't want to have these interruptions. So what we want to do in this research is to come up with a way that if there is a cybersecurity attack or there is a problem in the system that causes the energy management system not to operate correctly, the system can sustain itself. The structure of energy management system is centralized. So there is a central energy management system. All the units are communicating with that central system, and that central system decides how to manage energy for each unit. So it tells each unit, whether it's a storage, generator, or consumer, how to manage its energy use or storage level. There are decentralized ideas proposed, which essentially breaks this energy management system into a smaller energy management system. We think that with a cybersecurity attack, if they can target a single one of these, they can target multiple one of these. It is a good solution for many applications. It can even address islanding, but we want to go a step ahead. And what we are proposing is completely distributing the management, the energy management, in case of emergency, in case of a cyber attack or something significantly going wrong. So in that case, all these consumer units or generator units or storage units are going to be deciding for themselves. And as a whole, they will run the system without having a central system. The challenge is really the communication, because this is just in case of emergency. So there will be limited communication, we assume. And also there is the communication systems they have are not very broad. So the distance really decides that, because we don't want to waste a lot of energy on these communication systems. So the methodology we use is agreement protocol, which is from multi-agent system essentially, or it's known as consensus 2. So the idea is that if you look at this this node in the system, in this example, it's gonna only communicate with its neighboring nodes. So each of these units in the data center is going to be connected only to the units that are very close to it, and it's going to communicate only with those. And through essentially Laplacian equations, using Laplacian equations as state space for each node, we can mathematically prove that they can converge to a consensus that is average of the initial conditions, and assuming that the graph is weakly connected and balanced, which is a reasonable assumption, especially within a data center. Now, the issue is that we need some pieces of information that we want everyone to have. We want to know what's the average or overall amount of energy being produced, what's the overall being consumed. So if you're consuming too much, then these nodes on themselves, if they know that, they start lowering down their consumption. For example, if we are talking about lighting, they can dim the lighting, something that usually energy management systems do. But in this case, the lighting system itself decides that, right? So this is how this is the way we want to do it. Our proposed solution is for each node to share its energy production or consumption, right? So with its neighbors, right? And then through consensus, all the nodes will know because once they put that value to their neighbors and receive the values from neighbors based on algebraic connectivity. After some time, all the nodes will know the net average energy of the system. So they know per individual unit, what's the average? Is it consuming or generating energy? But they don't know the size of the network. They also need to know the size of the network, meaning how many nodes are in the network. And for that, we use a pattern similar to what they use in computer science for checking parity. And with consensus, with agreement protocol, that gives us the number of nodes. So everyone in the system, every unit in the system knows per unit what's the average energy usage, and how many units are connected, how many units are running right now. And with those two numbers, they can have a general picture. And then the next step is that we have a PI controller in each node to decide how it's going to react. The ideal is to keep overall energy consumption 0 or negative, having essentially generation to fill up the storage units. And specifically for the storage units, we have more complicated controllers because for them also state of charge matters too. And then this is just a sample of the results. This is a randomly generated generator graph with 500 nodes, not very connected for the purpose of making it a bit difficult. And we simulated 3 renewable generation units and 20 storage units, and tried the consensus, the agreement protocol, and it was successful. We have obviously more results, but because of the short amount of time I have, I can't show them. But we are not really done. That there is a lot more to do with this. What we want to do really dive into is, first of all, see the impact of algebraic connectivity, which essentially means that how much connected our nodes are, how many of these connections between the nodes we have. Like if you think of a tree, how dense is the tree? How dense is our graph? We want to do some contingency planning and look at some power system parameters there. So the idea is to it's a what if scenario. What if we have 3 different islands? What if we have just one island that have just one generator, right? Generator unit, can it survive, right? So we start, we look at different contingencies and see at what point our system cannot handle it anymore. And also we want to specifically look at islanding and kind of see, can we relocate the units and their distances in a way that the chances of islanding reduces, right? Which is a discussion from graph theory. With that, I want to stop here and have any questions from you. I wanted to keep it at 10 minutes. I'm not sure if I did or not, but I'm happy to answer questions.
You went a little bit over, but we're still good. So any questions? Again, you can raise your hand or write in the chat. I have one, Saeed. So what's the delay between once you come up with the best, most efficient node assembly and avoiding islands? What's the delay in implementation? Is it, is it a decade? Is it years? What's the delay?
what do you mean by really what really decides the time limit? So if the energy management system goes down, these systems can kick in right away, if that's what you're referring to. But the challenge is once the nodes put out, so the majority of work happen at the communication level here. So when the energy management system goes down, each node, let's say we have a storage, we have a battery unit. It wants to tell everyone how much energy is it generating right now, it's putting out right now. It's not going to tell everyone in the network, it's going to tell only its neighbors. So it's going to refer that information to a neighbor, and those neighbors are going to refer to their own neighbors. And that's going to, so it's going to take time before all this information propagates through the network. How fast that's going to happen, how fast everyone is going to reach to that consensus and feel like this is the number we are looking for, that really depends on that algebraic connectivity, how densely connected these nodes are. Right, so that, which is, like I mentioned in our future works, that's something that we have to look more into and see how it impacts our work.
Okay, thanks.
Sure.
At this point, I think it's best if we move on. And again, if you have questions, just put them in the chat, and Saeed and Anthony will do their best to answer them.